Welcome back to the 11th video of this course in quantum processing. Last time I talked about the idea of quantum error correction utilizing the idea of quantum system environment model, and also the operator sum representation that we used in order to extract errors and also correct them. Today is about how to quantum error detect. So suppose that we have some kind of code space work, some space, some vector space, or actually vector subspace, part of the Hilbert space. This vector subspace, under some errors, we can have maybe here just rotation. So here we may have E0 of some change or error by unitary transformation U, which is rotation. Which is R theta, for example, here just rotation. And suppose that maybe another issue that we have, error, that's like a projector. So suppose we apply some projection that occurs to perform maybe single subspace, which is much smaller than the subspace that this C occupied before. It can be even a dot, like we see here, a projector. Another or third one here, maybe we can apply phase damping operation that you have, so it's complete deformation. Okay, it's complete deformation of the subspace, as we see here. So we would like to detect the error, and this is a whole story about this. So let us just try to say something about the cross operators, or the error, or the elements of the cross operators in our system. So suppose that this EK conjugate, this element, this output result, is kind of disjoint of the subspace, disjoint of the whole subspace for all values of k. If this happens, it means that the elements of the error elements are kind of distinguishable. So distinguishability of the elements that we have for these error operators, it means that I have complete separation or disjoint of these elements from the whole subspace. This is important in error correction, as we see, and actually in error detection, because when we detect the error, maybe we can correct it. But here, let's take an example for this. Suppose that this is a code space work that we are interested in. C, this is C as a vector, and this vector spans the two zeros and tensor product 0, 1, and also another coefficients or amplitudes for 1, 0 and 0, 1, as we see here. And let's suppose that we expose a phase damping operation that is composed of the following. We already had that before, that these elements and these errors in the phase damping operation is about the square root. This is alpha instead of lambda. I'm here following the Ike Chuang's notation, and the square root of alpha times identity, and here 1 minus alpha times the z operation for the 1, for the error operation for 1. And let's apply that by the following. So here, if I look at the error elements for E00 as phase damping, is nothing else than the alpha II, right? What about 0, 1? You just take here square root of alpha times 1 minus alpha and IZ. And the same for E10 and E11, they are like the following. Let's apply that on the code space C of our system, and let's see the result. The result for the first one, for example, is nothing else than just to remember this state, that if I have E00 acting on C, it means that I have 00 acting on C is equivalent to E0 C E0 conjugates, right? So if I apply that case here, I find there's nothing else than alpha square c. What is the next? The next will be like this. So I just show the first result of the operation for E01 times C. If you apply that on C, you find that just getting something different, which is the sign. So it gets minus sign due to the operation, the flip operation of the phase. So you see that this is just different from C in terms of this coefficient, and also the signs for here, the signs, just the signs. Think a moment for yourself. You would like to calculate E10. Maybe you can look at it here. And this is for E10 times C. The difference between this state and this state, it just you have this sign. So I marked you just more or much blacker than the other, that this is just different in the minus sign. If you look, and actually times the conjugate of both, you can complete that. But the important thing that I would like to highlight here is that those kind of bases here, those, if you look at them precisely, they are orthogonal to C. Those are orthogonal to C. But it's actually E01 and E10, they are not orthogonal to each other. Okay, those guys are not orthogonal to each other, which means that some error, they are non-orthogonal to each other. It means that errors or an error occurred. We don't know what's this error or what this error really is, but it means that we have error, and this is a scheme to quantum error detect, and by this way it does not quantum error correct, just only quantum error detecting. So this was just a simple scheme for applying the concepts that we learned for phase damping and on 2 qubits, and the projectors and the cross operator quantum elements for E sub k sub j, as you see here, and this just a quantum error detection scheme. Thanks a lot for this video, and see you in the next time.